Okay, so let's take a look at a sample problem about the cyclotron. So it says, suppose a cyclotron is operated at an oscillator frequency of 12 megahertz and has a radius r. Okay, so what is the magnitude of the magnetic field needed for the deuteron? Deuteron means it has one proton and one neutron. Okay, so to be accelerated in the cyclotron, and the deuteron mass is roughly 2 protons, so because it is a 1 proton plus 1 neutron. Okay, so actually we just need to use the equation here. So use this one. Actually it tells you what is F oscillate. It also tells you the Q and also the M. So the only unknown is B here. So we can use it as a B equals 2 pi M F over Q, something like that. So here we have B equals 2 pi M F oscillator over absolute value of Q. And then, so we can just plug in the number. So it is 2 pi times 3 times 3, 4 times 10 to the minus 27th. And then times, this is 12 megahertz, 12 times 10 to the 6th power, all over Q. Q is, it tells you it is 1 proton. So we should be 1.6 times 10 to minus 19. Okay, so in this case, B is 1.57 Tesla. Okay. Yeah. So actually for B, what is the resulting kinetic energy of the deuterons? Kinetic energy. So to know the kinetic energy, of course we know the mass, so we would like to also know the velocity. So actually for the we have another equation here. So we have R equals to mv over qb. So here we would like to find v. So we move these 3 terms to the left side. So v equals rqb over m. So here we should have v should be R times Q over, times B all over M. And then we can just plug in the number. The R is 0.35, and then times Q is still 1.6 times 10 to minus 19. And then times B is this one, 1.57. Okay, 1.57. all over 3.34 times 10 to minus 27. Okay, so in this case it is 3.99 times 10 to the 7th power meter per second. So this speed is quite fast. It's quite fast. So for the speed of light is like 3 times 10 to the 8th power meter per second. So this is over over 1/10 of the speed of light. So yeah, this is quite fast. So let's see the kinetic energy. Actually, we don't consider the relativistic effect here. We just consider the classical effect. So we here just use 1/2 mv squared. Otherwise, if we consider the relativistic effect, it should be like gamma minus 1 mc squared. So gamma is like 1 over the square root of 1 minus v over c squared, something like this. Because v over c is sufficiently large, so yeah, this will tends to influence the kinetic energy due to the relativistic effect. But actually, in this semester, we will not cover the relativity in chapter 37. Okay, so yeah, just let you know a bit. Maybe later in this semester, I will just post the link on the website, on the course website. So if you have interest, you can check it out. Or yeah, okay. Of course, you can just find it in my YouTube channel. Okay, so we just use the classical kinetic energy, so which is 1/2 times 3.34 times 10 to minus 27 times V. V is actually this one, so 3.99 times 10 to the 7th power, quantity square. So finally, it should be 2.7 times 10 to minus 12 joule. And if you convert it to EV, so you just divide this number by 1.6 times 10 to minus 19, then it becomes 17 mega EV. So considering this unit, then the kinetic energy is not that large. It's not that large. Okay, so I think this sample problem is quite easy. Okay, so next we talk about another thing. So actually, it is I will consider this is still the Lorenz Force. Although it is not explicitly written in the textbook or in the slides here, but I will also consider this is the one type of Lorenz Force. Okay, so here let's see what it is. So here it says the magnetic force on a current carrying wire. So here we just fix a wire here and here, and then we also have external B field generated by something else. But here we just assume that there is uniform B field in the whole space, not only this area, actually in the whole space. Or maybe here is still okay. But yeah, so actually but I will consider it is in the whole space, because you need to consider the length of the wire. Okay, so I think we should consider there are B field in the whole space, and then it is perpendicular to the wire. So if there is no current, then there is nothing special. The wire is very straight to connect these 2 points. Okay, there is no force acting on the wire. Of course, you should neglect the gravitational force. And here, if we have some current going through this wire, then there will be something strange. There is something strange things happen. So here, if we have current going from bottom to top, there will be a force acting on the wire to the right side, so that the wire bend to the right side. And if the current is going from top to bottom, there will be a force acting on the wire pointing to the left side, so making the wire bending to the left. Okay, so it says a straight wire carrying current I in a uniform magnetic field experience a sideway force. So the force can be expressed like this. So FB equals I times L cross B. So so let's see how we can use this equation first. So I is very trivial. So this is nothing but the current going through the wire. So and And the next is L and B. B is still very trivial because you know what is B field. So B field is nothing but here. So in this figure, it is pointing out of the page, indicated by a dot. Okay, so for the L is the length vector that has magnitude L and is directly along the y segment in the direction of the conventional current. So which means that, so suppose we have a B field over the whole space. So here we will try to consider L has a magnitude. L is the length. L is the length of this wire, and the direction of this L vector should be the same as the current, which means that in this case we have L pointing upward. For the figure B, we have L pointing upward. Okay, so here L cross B, we can use the right hand rule. So you use your finger pointing to the top, and then cross it to the B field. The B field is pointing out of the page. So we will do it like this, and then your thumb will point to the right side. So this is the direction of L cross B. And as much as I is positive, so FB should point to the same direction as L cross B. And here for the figure C, I pointing downward, which means that in this case L is pointing downward also. So L is pointing downward, and then cross to the B out of the page. So your thumb will point to the left side. So here we have L cross B point to the left side, and also FB also point to the left side. And just now I just mentioned that we can really consider it is the Lorenz force. So when we consider the Lorenz force, it is something like FB equals Q times V cross B. Q times V cross B. So here we know that I should be something like dq dt. Okay, so here we have something like dq dt. So here it's like we divide by delta t, and then we also multiply by delta t to the v. So v times t is somehow like the displacement. So this thing is like I, and then v times delta t will be like L. So finally it becomes I times L cross B. So I would say this is something like the Lorenz force. And here we can really use the right-hand rule to determine the direction of the magnetic force, Okay, so here, so it says if the y is not straight or the field is not uniform, we can imagine the wire broken up into small straight segments. So if it is not straight or the B field is not uniform, then we just need to cut the wire into many small segments. So you can consider for every segment itself, it is straight, and the B field at that area is uniform, and then you can get dFB for every small segment by this equation, and then you just need to integrate all the FB on the wire so that you get the total force acting on the wire. So nothing special, something similar to what we have done before. Okay, so here is an other sample problem. So it says a straight horizontal length of copper wire has a current I through it, what are the magnitude and direction of the minimum magnetic field B, need to suspend the wire that is to balance the gravitational force on it. The linear density of the wire is this number. Okay, so here, this is the wire. This is the wire. The current is going out, so L is also pointing out of the page. And of course, there will be gravitational force acting on the wire, which is mg. So for high school physics, you should know this. And here we should imagine there should be a magnetic field or the B field, so that it will interact with the current, and then as much as there are current in the magnetic field, there should be some magnetic force acting on the wire. So yeah, so here we should determine the direction of the B field. So of course this figure already tells you that the B field points to the right side. So if you use right hand rule, L is pointing out of the page, B across the B, so your thumb pointing upward. So you know in this setting, FB is pointing upward, so which is opposite to mg. So if the magnitude of B is suitable, then FB and mg can perfectly cancel each other. So it asks you what is the magnitude and direction of the minimum. Yeah, so of course the direction is pointing to the right side. Okay, so the direction is pointing to the right side, and for the magnitude, we should have something like I times L times B equals mg. Actually, it can be not so. Actually, the B does not necessarily need to point to the right side. If it does not point to the right side, for example, it points to somehow like this. Maybe I just zoom in here. So maybe if B is pointing somehow like this with an angle with the plane, you see it can still generate the B field pointing upward. But here it asks you for the minimum magnitude. If the B field is pointing somehow to this direction, then the magnetic force should be ILB times sine of phi. So if phi is not 90 degrees, then sine of phi should be less than 1. And then you need to increase the B. So here it asks you for minimum magnetic field, so you should assume that B and L should perpendicular to each other, so that sine of phi is 1. Okay, so that you can minimize B. Okay, so here ILB equals mg, and then what is the unknown? The unknown is B, so we just move IL to the right side. We have B equals mg over IL, so we can just plug in the number. So actually we don't really know M. We only know the density of the wire, which means that M should be this number. This number should be 0.0466 over L. Or you can consider M over L. Sorry, I should say M over L should be 0.0466 kilogram per meter. Okay, so yeah, so we can just regard M over L is this number. So we have 0.0466 times 9.8, and then over I is 28. Okay, so this is 1.6 times 10 to the minus 2 Tesla. Okay, so this is the answer. This is the magnitude, and the direction should be pointing to the right side in this figure. Okay, so here is almost the final part of the chapter. So here we talk about the torque on a current loop. Okay, so here suppose we have a current loop like this one, or maybe the other way around. So this should be like this, should be like this. Okay, so this is the axis to be rotate. So this current loop is connected to this axis. So this axis can rotate. Yeah, and here we have a magnet bar. So this is the north side, this is the south side, and it will generate the B field pointing to the right side. And if it is between these two magnet bar, we can assume it is like uniform. So it is somehow like the capacitor, but in the magnetic version. Okay, so it generates the B field pointing to the right side. And here we try to apply some current going through this loop. Okay, so there will be some interesting thing happen. So it's like a motor. So as you can see, okay, actually I think for the left wire, you can see the current is going pointing to this side. The current for the okay. So let's for the current on this wire. So it is pointing to the bottom left. It's pointing to the bottom left, and of course shown as the L vector. And then B field is always pointing to the right side. So here we can apply the right-hand rule to determine the force. So L is pointing out of the page, and then B is pointing to the right side, so like this, and then your thumb will pointing upward. So which means that the F acting on this wire is pointing upward. Okay, so and next for this wire, the I is pointing to the top right. Okay, so your thumb, your finger points into the page, and then B field pointing to the right side. So using the right hand rule, your thumb pointing downward. So here we have the F pointing downward. So this side pointing upward, this side pointing downward. And for this wire, okay, this wire is parallel to the B field. So L cross B will be 0. And similar for this one. So there is no force acting on this wire and this wire. So yeah, so you can see that if we fix this point and this point, the force is going this side, and then this force is going downward. So in this case, this loop will rotate clockwise. It will rotate clockwise. There will be a torque acting on this loop. Okay, so this is the cross section of this figure. So here, for this wire itself, you can only see a dot, and so as this wire is here. So one force acting on this wire pointing upward, one force of this point pointing downward, and then this is the fixed point. Okay, this is the axis to rotate. So it will rotate. Okay, so actually this is the torque. Denoted as NIAB sine of theta. Okay, so let's see what does they mean? What do they mean? Okay, so for the first one is capital N. Capital N means the number of turns. So if there is only a single coil, so N is 1. But usually the N may be larger. Okay, so this is the number of turns. So I don't think we have a unit for it because it's just a number. You count how many turns. Okay, so next I is the current going through this loop, and then A is the area. So here is a rectangle. So you can easily find the area, the cross-section area of the coil. So we have NIA, and then B is the B field magnitude, and then sine of theta. Sine of theta is the angle. Sine of theta is the angle between the magnetic field and the normal vector of the coil N. Okay, so here, suppose this is the coil. This is the coil. So we can draw a vector which is perpendicular to the plane. And you may still ask, we can either define n point to this side or the other side? Can we make n point to the bottom left? The answer is no. The answer is no. But how can we determine whether the n should point to the bottom left or top right? The answer is you can apply right-hand rule. You can still apply right-hand rule for it. So how to apply right-hand rule is slightly different from working it on the cross product. So how we apply the right-hand rule here is you try to use your finger, follow the direction of the current. So it is something like this. And so your thumb will point to the direction of the normal vector. So in this figure, it is something like this. So for the one closer to you, it is going from top left to bottom right. And then for the wire behind, it should be going from bottom right to top left. So it is something like this. And then if you use the right-hand rule, it should be something like this rather than that. If the current is going to the other direction, which is something like this, then if you apply a right-hand rule, it should be something like this. Your thumb will point to the opposite direction. But for this figure, so using the right-hand rule, it should be something like this. The normal vector point to this side. And for this one, it's something like this, your thumb point to that side. So you use right-hand rule to determine the direction of the normal vector. And yeah, so actually this normal vector has the same direction as the torque. So yeah, you can also use right-hand rule to determine the direction of the torque, because torque is also a vector. It's also a vector. Okay, so here we define another variable called the magnetic dipole moment. We use the Greek letter mu to denote the magnetic dipole moment. And actually, the magnetic dipole moment has a direction has the same direction as the normal vector. So which means that you can use the right-hand rule to follow the direction of the current, and then your thumb will point to the direction of the magnetic dipole moment. And the magnitude of the magnetic dipole moment is n times I times A. So which means that it is the cross-section area, the area of the coil multiplied by the current, and then multiplied by the number of turns. So it is the magnetic dipole moment. So you can see here, as here we have the sine of theta. You should imagine something like a cross product. So this is a vector, and then cross with this vector, and then the theta is the angle between this vector and this vector. So for the scalar form, it will be like one magnitude times another magnitude, and then times sine of theta. The theta is the angle between these two vectors. Okay, so if we define mu to be n times I times a, and yeah, of course, the direction of mu is also the same as the normal vector, then we can also write it as tau equals mu cross b. Tau equals mu cross b. So in chapter 22, when we talk about electric dipole moment, we have something like this. The only difference is that this is the electric dipole moment rather than magnetic dipole moment, and all the thing will be the same. So we still have a torque equals the dipole moment cross with the field. Of course, at that time it is the E field. Here we have magnetic dipole moment in the B field. At that time we have an electric dipole moment in E field. So mu cross E, and here we have a mu cross B. Okay. I think at that time we don't use mu for the electric dipole moment. At that time we use P for the electric dipole moment, if I remember correctly. So the formula will be something like that. And for this one, this is the energy stored in the system. So yeah, it is a dot product, and at that time it is like U of theta is like a negative P dot E, something like this. So they look quite similar. Okay. Okay, so here is the last sample problem in this chapter. So let's see. So it says a circular coil with 250 turns, an area of A, and a current of 100 mu A. The coil is at rest in a uniform magnetic field and magnitude B, with its magnetic dipole moment initially aligned with B. So in the figure, what is the direction of the current in the coil? Okay, so here, of course, we should use the right-hand rule to determine the direction of the current. So as I mentioned, if we know the current of, if we know the direction of the current, so we can use the finger follow the current, and then your thumb will point to the direction of the normal vector and also the mu. So here we know the mu. So we use the thumb pointing to the direction of the mu, and then your finger will just follow the direction of the current, which means that the current is something like this. Something like this. So this is a cross section. So, but yeah, I need to draw something like 3D. So for the one behind, it is going upward. For the one closer to you, then it is going downward. So it's something like this. Okay. So this is the direction. The direction is something like this. The current. Okay, and this is mu. Okay, so B. How much work would the torque apply an external agent have to do on the coil to rotate it 90 degrees from its initial orientation, so that mu is perpendicular to B and the coil is again at rest? Okay, so here it assumes it is at rest and at the beginning and at the end, so which means that there is no angular momentum or no angular energy in there. So there is only a potential angular energy. So which is like WA equals U of 90 degree minus U of 0 degree. So yeah, because it is from its initial orientation is rotate to 90 degrees from its initial orientation. So for the initial orientation, moment initially aligned with the B, which means that it is at the beginning the theta is 0 degree, which means that they are the two vectors are aligned, which means they point to the same direction. So in that case, the theta is 0 degree. Okay, so here we would like to make it have a 90 degree angle between each other, and then finally it will rest. So there is only potential energy. Okay, so it is like a negative mu b cosine of 90 degree minus mu b cosine of 0 degree. Okay, so here cosine of 0 degree is 1, so this is 1, and then cosine of 90 degree is 0, so the whole term you can just make it 0. So finally it is nothing but mu times b. So, and mu times b is nothing but n times I times a, and then times b. So this is mu. Okay, so we can just plug in all the number. So actually n is 250 turns. So n is 250, and then times I is this one, 100 times 10 to the minus 6 power. Okay, this is I, and then A is this one, 2.52 times 10 to negative 4, and then times B is 0.85. Okay, so the answer is 5.36 microjoule. Okay, so far any questions?